Hello, I'm David. It's semester 1, 2022, and this is a multivariable and complex calculus revision seminar. And I've had some requests, and I might get some more later, but I'll try and talk about those things. Okay. I just want to tell you a bit of history about suffix notation for myself, my own history with it. I had never seen it until it appeared in MCC in 2019. It's apparently very common over in physics. One of the reasons I have it in this is because a lot of people in the physics degrees do this course, but also the person who wrote it came from a physics background. And so, yeah, all right. So I'm going to tell you what I understand about it so far, which might not be complete, but it's a little better than it was 3 years ago. So my first understanding of suffix notation is, as much as it is technically possible to use it in any number of dimensions, it tends to only be used in 3D. So it borrows from the tradition in linear algebra of representing something like a matrix by a little letter or any letter at all with subscripts to tell you what position you're in inside that thing. And so you might have something like a matrix A, and then its entries are called A, I, J, like that. And so the I tells you where you know, row I, column J, and here you are at position A, I, J. And that's pretty much it. So the way that suffix notation is used is to somehow, well, my understanding of it, the way people use it, is that they don't really distinguish between the matrix as a whole and its entries. And so when you just write a bold statement of, you know, with nothing around it, of just, you know, A, I, J, like that, this is representing every specific entry of the matrix A, the one that's in position I and position J. Maybe not every, but any. And when I write this, like, that is of vector V. Cool. That's just the beginning of that. So what suffix notation is designed to do is to tell you about the entries of a new object you make out of other objects. So this is sort of the situation. So you make a vector out of other vectors. And you tell the person reading your thing, the reader, or yourself probably, because it's designed to do in calculations, what its entries are. And the thing is that many of the operations that act on things like vectors and matrices involve sums. So when you do matrix multiplication and you figure out a specific entry, you take the row of this one and the column of the row of this one, the column of this one, and you multiply the matching bits and you add them up. And so that add them up bit is a really common part of doing operations on matrices and vectors. And so it's so common that we're not even going to write it down as a sum. We're going to assume that there are sums involved. Okay. That's what we expect right from the outset. There will be sums involved. So and I just need to point out that like all notation, mathematical notation has lots of different purposes, and one of them is for naming things, and one of them is for describing things, and one of them is for making calculations easier. And so suffix notation is specifically designed, as far as I can tell, for making proof-like calculations involving vectors and stuff easier to write. So the thing that makes notation can make calculations easier. I mean, algebra did that. When people invented algebra, in the sense of, using letters to represent things, we chose, well, we didn't choose, it sort of just happened, but the notation that has survived has been notation that you can manipulate directly and have rules for manipulating the notation itself. That's easier than thinking about what's really going on. If you just follow the rules, you'll get to an answer at the end and it will be the correct answer. That's the purpose of suffix notation. And one of the reasons it feels like there's no understanding involved is that that's the point of notation. The point of notation is once you've set it up and you know what it stands for, you can do manipulations on it without thinking about what it stands for, and then just at the end, look at what you've got. That's my understanding of what its point is. But I'm just making that up based on observations of the way the lecturer asks assignment questions. So, okay. That's something I just have to hold on to, that the point is to be able to do manipulations without having to think about it. So what it does is it removes all the sum signs and makes it look like it's just multiplication and addition. I don't know if this is a goal, but it's the truth. Remove these things. It makes it look like multiplication. Okay. Cool. It's just going to be easier for me to just do an example. Write the end. I've got 3 by 3 matrix A, B, and C. Write the entries of the matrix A, B transpose C in suffix notation. I'm pretty sure this was one of the tutes or something like this. I'm just making up something up that seems reasonable. Okay. So, right. I know that the entries of A, B transpose C will be something sub ij. There'll be a row for I and a column j, and there'll be an entry in that position. So that's what I'm imagining in my head, that AB transpose C is a matrix. It's a 3 by 3 matrix because A and B are 3 by 3, AB transpose is 3 by 3 times C also 3 by 3. So it's a 3 by 3 matrix. It has entries. So you need I and J to locate an entry. So that's what I'm imagining. So it seems to me that I should give this matrix a name so that I can talk about it. And so what I want is to write Mij equals. To say the matrix M's entry in position I and J is going to be equal to something. So what I want here is something that if I did all of the sum notations would still have an I and a J left to tell me what position I'm in. That's an important goal here. I want to tell someone what the entries of this matrix are. There is a different one for every combination of I and J, so I need to keep the I and J eventually in my formula. So the rules of suffix notation are that any time a subscript is repeated, then that tells you there's a secret sum that you haven't written on the page. But if a subscript only appears once, then it's still going to be there at the end of the calculation. So I'm going to write an expression here that will involve an I and a J once each. And every other suffix that appears is going to have to appear twice because the final thing I want only is allowed to have an I and a J. How are people feeling about what I've said so far? Okay. All right. This is my goal. With one I, one J, and pairs of other subscripts. That's the plan. Yep.
Do you mean that I and J should only appear once in total or once in like a...
Once in total. If there's a plus anywhere, then it's allowed to appear once in each of those pieces.
Okay. So
once in each term.
Okay.
But I'm hoping to do this in one term. But I'm going to go pairs no. But yeah. No. In each term is okay. All right. I don't know how to do this yet, so I'm just going to think about it. When I do matrix multiplication, so I'm still thinking about things. I don't know what's going on yet. So if I have the matrix A, then and the matrix B, then the entries of the answer for AB are going to be each row times each column, and I'm going to multiply the matching entries and add them up. So entry, I'm going to have to do it with an IJ at the moment, but I'll just fix it later. So entry IJ of AB is row I of A times dot product column J of B. That's how you do matrix multiplication. And row I of A would be A, I, and we're going to need a new letter to say where I'm up to in row I. So I shall call it K. And column J of B is going to be B, K, J, like that. So what this will do is I'll be here at AI1 and AI2 and AI3 and B1J, B2J, no, just a second. Yep. And B3J. And then I'll have AI1 times B1J and AI2 plus B2J and AI3 times B3J. And so I've got the numbers 1, 2, 3 and 1, 2, 3, and the ones have to match with the ones and the twos have to match with the twos and the threes have to match with the threes. So I've got these two Ks which match each other. And I'm going to add them up, but that's okay because I've got two Ks. That's the secret code which tells you that there is a sum here that I haven't written down. So that's how to do matrix multiplication. Okay, all right. So Mij, bear with me, is the matrix AB transpose IK times the matrix CKJ. So whatever this matrix is, its entry in position I and K is multiplied by the matrix C's position KJ, and then all the ones with the same, we'll go along row I of this one and row J of this and column J of this one and multiply the matching spots and then add them up. So that's what it is so far. It's not in full suffix notation yet because I've still got a matrix multiplication here, but that's good. All right. So the next thing I want to notice is that the transpose here is the same as switching all the rows for columns and all the columns for rows. And so the transpose's position IK is the same as the original matrices position KI. That's what the transpose does. How are we feeling?
Is that going to affect how you represented like AB above, or do you just speak of that as the transpose happened on the outside?
Transpose happened on the outside. So this became this. So this is one of our rules. Matrix transpose interacts with suffixes like that. And then AB, according to this rule, the IJ entry of AB would be AIK BKJ. So these two things, I've got a K and an I. So I'll have A, K something and B something I. And then I'll have to put a new suffix in there to keep track of where I'm up to inside that matrix. So M, say. So this thing became this. The K and the I separated, and I put a new suffix in between them because that's how matrix multiplication works. This I and J separated, and I put a new suffix in between them. And I trust that that works no matter what the letters are called because they're eventually going to be replaced with the numbers 1, 2, and 3. How are we feeling? And now it's in full suffix notation. I can leave it like that. And also worth pointing out, I can now rearrange the order of these pieces and it won't change the answer. That's one of the main purposes of suffix notation, is to treat it like multiplication. I can now put this A over here if I want, and it won't make a difference to the final answer. And just to check, just making sure, I've got a K here and a K here. It appears twice, so it's going to be summed eventually at some point, and the K's will be replaced with the numbers 1, 2, 3, and there'll be an addition. I've got an M here and an M here. That's going to cause a sum. So when I've finally finished what this calculation actually represents, there will still be an I and a J, but the K's and the M's will be gone because they will be replaced with 1, 2, 3 and added up. So I still have the same number of I's and of suffixes here as I had here. Cool. So I found this, that when I helped people with this in the Maths Learning Centre this year, this was the most productive example I'd ever done to help me understand what suffix notation is doing. But there's more. So in order to ratchet some of the things that we're familiar with into suffix notation, they have created some extra notation to help us do that. But just as a summary of things we know so far, we know that matrix A and B, then the matrix AB, IJ, is AIK, BKJ. They are its entries. We know that so far. And also secretly in there, we have a dot product as well. Vectors U and V. then the vector u dot v isn't even a vector, it's just a number, and it is ui vi. Because we run along u, its entries, and we run along v, its entries, and we add them up. So at the end of this calculation, there will not be any i's left because it'll be a sum, but that's okay because u dot v is a number. It's just one number. It doesn't need any i's to tell you where you are in it because it's just a number. Cool. All right. Oh, and transpose. That was good. We did that too. Matrix. Like that. So your suffix notation vibe is you're going to be a bit sloppy about things. You're going to pretend that the matrix M is the same as just its entries, which is a slight break with philosophy, because back we used to thought a matrix is a thing and that thing has entries. But in suffix notation, the matrix is its entries. Okay. So things we don't know is how to do the cross product. I mean, we do now that you've done this course, but the cross product is a bit trickier. There are sums involved in the cross product, but they're only, oh crap. All right, I'm just going to leave a gap. And I'm going to number my pages because last time I did a revision seminar, I got them all mixed up. So. Okay, so we've got some things. I'm actually just going to put this page elsewhere and come back to it and fill in some more things in a minute. Okay, now this is a bit where I'm a bit hazy off the top of my head. I'd have to look up some notes probably. There is a brand new, here we go, here it is. The matrix, which is the identity matrix. Has these entries. So that delta, yep. Of course it is. No, it does not have to have the same dimensions. But that is what it is. And this is what it's borrowed from. So it's just easier for me to think about it this, but you know, but more general than that. But that's what it does. When you've got delta II, you get the answer 1. And when you've got delta ij, where I isn't equal to j, you get the answer 0. Cool. So what that means is that delta ij times ajk is aik. Like it doesn't change, multiplying the identity matrix doesn't change a matrix's entries. But it might change which one you're talking about today. But this is the matrix identity times A, which is totally the same as the matrix A. And this is the IK position. Oh no, sorry, damn it, IK. This is the IK position of I times A, and this is the IK position of A. But as our friend over here tells us, that these are not, it doesn't necessarily have to be matrices, but it'll work for matrices. And we can borrow what we understand about matrices to remember how it works. So the IJ position of the matrix IA is delta IJ AJK. That's how you do matrix multiplication. Normally you put an I in this spot, but we have a special symbol for that. It's called delta. And this is the IK position of the matrix A. And this is the matrix A, IA. And so it works out that way. And so what the delta does is it replaces this j with an I. And we also have delta ij of vi. This is position j of I times v, which is position of j of the vector v. Because vectors are columns, right? So what that means is now I've looked at what it does with matrices and vectors, and now over in physics where we have things that are bigger than matrices and vectors and things that we don't even know what they really are, as long as we've got subscripts, we can now know that when you multiply delta ij with anything, it replaces all the j's with i's. Now we have a manipulation rule that we can do on the symbols on the page without having to think anymore about what it means and just worry about what it means when we get to the end. Which is a very physics vibe, right? You go, when you learned Newtonian mechanics and you go, here are all these equations that represent how these things work, I will do the algebra of solving equations and not really worry about what any of the symbols and quantities mean at this time. And at the end, I'll go, aha, the time is 7 seconds. Great. And I know what that means, but I won't worry about what any of the symbols I write in between actually mean. How are we feeling? Okay. Cool. Okay. I believe there were rules about what deltas did, like multiplying. Oh no, that's the epsilons and the deltas, isn't it? This is the only rule I know off the top of my head of what the deltas do. So now we have in our head a new rule which says delta ij times any crap replaces j's with i's in this crap here. Probably only in the thing right next to it, I'd say. That's what it did here. I's with j's, damn it. Or j's with i's, whichever of them is around.
It doesn't matter like if it's in the row or the column spot, it's just that same.
Yeah. Then it replaces it with the other one. Yes, I'm glad I did them both this way because it does covers both. So it doesn't matter whether it's the first one or the second one. Whichever one of these appears here, it replaces it with the other one. So the one that here appears as an I, it will replace it with a J. And that's because delta ij is the same as delta ji, because the identity matrix is symmetric. Yes. Okay. So you could do it in 2 steps if you wanted. All right. Sweet. I'm so excited. So the last thing I know for sure is that there is a new thing. What about the cross product? Because the cross product is like weird ass thing, right? I just want to be sure I know how to do the cross product. So if I have like A, B, C, actually I should give them names. Just a second. So V1, V2, V, let's call them U, sorry, U1, U2, and U3. Cross with V1, V2, and V3 will now be so I'll get U2 V3 minus V2 U3. And then the second coordinate will be U1 V3 minus V1 U3, except I'll have to minus that because it's in the middle. And then the third one will be U1 V2 minus V1 U2, like that. That's the cross product. You can do it with an IJK up here and the determinant, but I like to do it this way. I've practiced it long enough. I didn't see the cross product. So when I was at uni, I didn't see the cross product until third year. Maybe I probably saw it in multivariable calculus. I don't remember it though. I remember doing it in third year and going, what the hell? Obviously I blanked it out. Maybe MCC was in third year in those days. I did do Chinese all the way through, so I didn't do all my second year courses in second year. I didn't do all my third year courses in third year, so I had some extra ones to do in honours, which was nice. But yeah, I was most surprised. And my lecturer was like, "You've never seen the cross product?" And said, "Well, you wrote the curriculum in first year, you would know." So anyway. So you can do it like this. It is traditional when they do this thing. Like that, yeah? Okay, so these are sums, right? This is the sum of two pieces. Which don't match neatly, right? I've got a 2 and a 3 here and a 2 and a 3 here. That's good. So what they've created, I don't like it. They do match, and there's, of the possible ways of multiplying pieces of this with pieces of this, of which there are 9, we only have 6 of them in this formula here. And in particular, with we're definitely missing U1 V1 and U2 V2 and U3 V3, which would be in the dot product. And so if I want to write this in suffix notation, I have to somehow turn this sum, all of these sums have to look exactly the same. That's how suffix notation works. Every entry of the matrix has the same notation for every entry. So all 3 of these have to look identical when you write them in suffix notation. And somehow I have to make this look like it's the sum of things where some suffixes match. And we do that with the magic of this thing. This had a name. Was it named after somebody? Cool. And if I've got it right, I'm pretty sure, let me just check this. It's 0 if any pair of them match. And it's 1 if it's I, J, K, or they're in the correct cyclic order, right? J, K, I, or K, I. K, I, J. And -1 if they're in the reverse order. Damn it. Just switch any 2 of them and it'll be okay. Like that. Is that right? Let's wait. And that covers all 27 options. Apparently. Because there'll be 3 where they're all equal, like epsilon 1, 1, 1, and there'll be epsilon 1, 1, and then not 1, of which there are, I get 2 of them equal, so you have to pick what one they are, and there's 3 options for that. So you have to pick which ones are going to be equal, and there's 3 options for that. What that one is, and there's 3 options for that, and then 2 options left for what the other one is because it's different. 18 plus 3 is 21. And then there's 6 more. Yes, that's all of them. Okay, cool. All 27 options. Almost all of them are 0. Cool. Who knew combinatorics would come up? I just wanted to be sure that they're all there. Okay, and so someone's going to have to remind me how to do the cross product. If I've got U cross V, position I is going to be, I'm just guessing. Is that right? Yes. Okay. Yep.
In the notes it says epsilon ijk is positive if ijk is like representation of 1, 2, 3. Are they just like labeled?
Oh, crap of all. No, 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 I was wrong. I was wrong here. You're right. 1, 2, 3. So ijk is 1, 2, 3, or 2, 3, 1, or 3, 1, 2. ijk in that order is 1, 3, 2, or 3, 2, 1, or 2, 1, 3. Sorry. Yep. The ij and k are not ij and k. They are literally the numbers 1, 2, and 3. Yep. Yes.
Because it's like cross product is 3 dimensions. So
Yep. As I said, it usually works when the suffixes only have 3 options, 1, 2, or 3. Because the vectors themselves have 3 entries, because you can only do the cross product in 3D anyway. So let's just check that this works for the first coordinate. I just want to check. U cross V1 should be epsilon 1, 1jk, ujvk. That's what it should be. So I'm going to have to run through all the options for what j and k could be. So since the j's are repeated and the k's are repeated, I'm going to have every possible combination of j's and k's, of which there are 9. So it's going to be epsilon 1, 1, 1, u1, v1, and epsilon 1, 1, 2, u1, v2, and damn it, I ran out of turn. Just a second. So epsilon 1, 1, 1, u1, v2, and epsilon 1, 1, 2, u1, sorry, u1, v1, v2, and epsilon 1, 1, 3, u1, v3, and epsilon 1, 2, 1, u2, v1, and epsilon 1, 2, 2, u2, v2, and epsilon 1, 2, 3, u2, v3, and epsilon 1, 3, 1, u3, v1, and epsilon 1, 3, 2, u3, v2, and epsilon 1, 3, 3, u3, v3. I've run through all the options for what j and k could be and every combination of them, and I've added them all up. That's what suffix notation is doing. I can't do it one step at a time because this has got both a j and a k in this object here. So I have to do them all at once. But this one is 0, and 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 this one is 0, because they have a 1, 1. Oh, that one's 0 as well. Yep. This one's got a 1, 1 and a 1, 1. It's got a 1, 1, 1, 1, 1, 1. It's got a 2, 2. That's got a 3, 3. Cool, 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 cool. And this number is 1 because it's 1, 2, 3. That's in the correct order. And this number is minus because they're in the wrong order. It's 1, 3, 2. And so I get u2 v3 minus u3 v2, which is the correct answer. Yay! But we don't have to ever do this calculation again because we can just trust that it works. we can just trust that this is the cross product. This is the I entry of the cross product. And now, from now on, anytime there's a cross product, even if that cross product has stuff done to it afterwards, we can just write this as if it was multiplication. This is a supremely clever and strange thing to do, but mostly clever. We're gonna pay the cleverness of it. It's just like, you know, it's like slack variables when you're in Maths 1A and you go, hey, this problem is hard. Let's add 4 more dimensions. Now it's easy. And like, this is hard to write down. Let's write down a symbol that means that we're summing together 9 things, but actually only 2 end up coming out in the final answer. Like, it's just so stupidly cool as a thing to do. Yeah. And so we can go back to here and we can now say that U vectors U and V, U cross V position I is epsilon I j k v j u j v k. Right. Great. And then there's all these rules that turn epsilons into deltas and crap. I don't know how they work, but I don't know what they are. We can look them up. I want to put them on the. Sorry? I'm going to write it down, but I don't have any practice using it. So the contracted epsilon identity is that when you multiply 2 epsilons together, here we go. So just checking here, the only position that matches is the I. Yep. And so this thing should be equivalent to another thing that doesn't have an I in it, but it's going to be required to have J's and K's and L's and M's. And apparently it is delta JL delta KM minus delta JM delta KL. So what did we do? We basically switched the M and the L here. So I'm just comparing the IJK here. This J and this K is separated into the 2 deltas. They both, one has a J and the other one has a K in both terms. And then the L and the M are here. And in this one, they're the opposite way round. And this is apparently a thing that helps. I can imagine doing the dot product of 2 cross products, and this would appear. I'm just going to make something up just a second. So just made up example. Okay, second. U cross V dot V cross U. I know exactly what the dot product of U cross V and V cross U is going to be. It is going to be minus the length of U cross V. Right. Because these 2 vectors point in opposite directions. But I just wanted to, so this is a number. So I don't need to worry about the I's and saying position I because it's just a number. So let's just do this. This is going to be epsilon I j k times U j v k. That's what position I of that thing is. And then I'm going to have to multiply by position I of this thing. But I've already used K here. and it's all going to be part of a product. So I'm going to need to use new letters. So I will use M and N because I don't like writing L's. No, I won't. I'll use L and M so that I can use this thing. Like that. No, the V's first. Yep. Okay. So this is what position I of that thing is. And this is. Yep. So I don't need a dot product here because this I and this I mean that I'm multiplying the matching entries and adding them up, which is what the dot product is. Is that what you're asking? Yeah. Yeah. And now that it's all multiplication, I can rearrange stuff in whatever order I like. I have no idea if this is helpful at all. I'm just playing around. That may have been a bad idea, but anyway, here I am. And my identity, that's the contracted, I don't know what it was called, can't remember. This identity that turns epsilons into deltas means that I should be able to replace this with that, and it's hopefully going to be useful. Not enjoying it at this time. I did warn you at the beginning, I didn't know where it was going to go. I'm pretty sure you're allowed to expand it out the same as you do with addition and multiply with type stuff. Well, this and this will turn that M into a K. And this will turn that L into a J. I'm just going to rearrange them just to be absolutely certain. Oh, it's gorgeous. Sorry, just a second. The dot product of, okay, it's okay. I have no idea. I still have no idea. I'm so excited to see where this is going to go. So this JL, well, that's not what I wanted. Oh, crap, just a second. Where'd my J? That's a U. VL, VK. That's not a UK, that's a UJ, sorry. Yeah, okay. So, such a good idea. So, VLG, I should have done it with VL uj, shouldn't I? Yes, there we go. So now I've got, this is going to turn that L into a J. I've got VJ, UJ. And this is going to turn that M into a K. I've got UK, VK. And this is going to turn that J into an M. I've got UM, UM. And this is going to turn that K into an L. I've got VL, VL. And this is V dot U. And this is U dot V. And this is the length of U squared because it's U dot U. And this is V dot V. And so I've got U dot V squared minus the length of U squared, the length of V squared. Ah, oh, that's just so cool. Huh. I did not expect that to turn into anything good. That's like the Cauchy-Schwarz thing, right? Cool. All right. Yes, you can. All right. I'm going to stop for a moment. Thoughts, questions? All right. I think the Cauchy-Schwarz inequality says that this is always less than this. And so you're guaranteed this is going to be a negative number, which I said at the beginning is going to be minus the length of U cross V. Yeah.
Why is that something like that's useful?
I don't know. I was just playing around. I don't know. I was just trying to understand the notation. Usefulness is, well, I don't know. I'm sure it's useful. I can imagine some sort of physics, electromagnetic stuff where there's cross products flying all over the place, and it would make their proofs easier to do than with lots of sum signs. That's it. But I don't have enough experience to say why it's useful, but I can play with it and go, oh, this is something I recognize. So yeah, and this move where I could turn the deltas, match this delta with these things and this delta with these things, and therefore recognize something that I had recognized what it meant. That was a cool move. And I'm not against learning things just for the coolness of it. It does tend to sully the being examined on it, but yeah. All right. Are people okay if I move on from suffix notation? I'm just glad that I have a revision seminar on it now for future years. But next year I can watch it again and go, oh, I remember. I just have a question about before I move on from that. Were there any like assignment questions that asked you to do things with suffix notation? Sorry? Yeah. And then I just sort of didn't turn up again?
It was in our, there was one in our mid-semester test.
Yeah.
It was very confusing. Yeah.
I can imagine it would be very easy to poorly word a question.
Because they were like, prove that the gradient is equal to something, right? I forgot what it was. But so most people proved it exactly. But they were referring to a specific function.
Oh, right.
That was not very clear.
Right.
Whether they meant specific functionalities.
Yeah, so I was not starting putting the G from like, oh.
All right, cool. Okay. So the other thing, I'll be putting the notes on the website. I haven't been able to do it for the last couple of years because IT wouldn't let me, but I've just put it in a Google Drive folder. So you'll be able to get the notes that I wrote later. Okay, let's talk about limits of integration. Possibly other integration stuff if you want. I just have an example from probably the notes that I just wanted to talk through. It's just easier to do this with examples. So the mean value of the function f of x, y, z, which is x, in the tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, so I'm going to separate two things about this. One is what the mean value means. So mean value should mean the integral of the function divided by the integral of by the volume of the space. If it was the mean value of a 2D function, it would be the integral of the function divided by the area of the space. Okay. So when I integrate something, I'm going to need to do two things. I'm going to need to locate every point in the thing I'm integrating across. That is the first and most important thing I need to do. I need to locate every point in the region. I need a consistent way of telling people what every point in the region is. Right. So you can either parameterize the region, which causes you to need to deal with things with the dx, dy, dz, or you can locate everything based on their x and y and z coordinates. But you have to have a way of telling people how to choose every point in the region and not choose any points that aren't in the region. So what I mean by locate every point in the region, I mean you have to choose every point in the region one coordinate at a time. When you parameterize, you change the coordinate system and you still choose things one coordinate at a time. Okay. That's what I mean. So this region, I'm going to need to imagine what this region looks like and imagine choosing one coordinate at a time. And it may be that the choice you make earlier for the earlier coordinates changes what the choices are for the later coordinates. The reason I'm writing this stuff down, it's not because you have to, but so that when someone comes to this revision seminar and doesn't feel like watching the video, they'll be able to read it. So it may be that earlier coordinates change the options to choose for later coordinates. And that's an important point about how we do this. And so I want to say this to set up to look for it when I do this example. Okay, so first I'm going to have to find this tetrahedron. Now, what I'm about to do is not necessary or even possible in an exam, but I'm still going to do it. Oh, am I going to be able to see all of it at once? Yes. Just a second. A little less crap in the way here. All right. So that's going to be my x-axis. That's my y-axis. And then up here is my z-axis. So I can turn this any way I want. Many lecturers traditionally draw the x-axis here and the y-axis here and the z-axis up that way. I might usually draw it around this way. But, oh, wow, that's really weird on the video, isn't it? Sorry, that's just, there's some optical illusions going on there. Okay, so I have the point 0, 0, 0 just here, and the point 1, 0, 0 here, and the point 0, 1, 0 here, and the point 0, 0, 1 here. And so in terms of my tetrahedron, maybe I won't. Maybe I'll just not that point at all, this point. And of course, I do need the sticky tape. Gives you time to write notes and chat for a bit. All right. That's our tetrahedron, this space down here. I really wanted to bring a really big one so it's big enough for you to stand inside it, because the space that you have is fine. Where your body is in space is a forgotten sense that people don't realize they have. Okay, so there it is. That's the point 1, 0, 0. That's the point 0, 1, 0. That's the point 0, 0, 1. And it's this pyramid down here underneath that. That's what we're finding. We're going to have to find the volume eventually, but we're not actually finding the volume of that shape. We're finding what the average value of x is inside that shape. So I'm guessing that the value of x inside this shape along the bottom here is mostly 0. And so I'm going to get a number that's a lot less than 1, I expect, because the value of x, there's a lot of places inside this pyramid where the value of x is close to 0, and not many where the value of x is close to 1. So I think the value should be quite close to 0. That's my guess on average. That's, there's a lot of places here where it's close to 0 and hardly any places here where it's close to 1, the value of x. Okay, I'll bring back my thing. How are people feeling about my thing there? All right. If you're ever in the Maths Learning Centre and one of the staff is doing stuff with you, say, have you say to them, have you considered using the stuff in the cupboard next to the floor graph? That's where it's all kept. If you ever want to play with these things, then just ask. Okay, so cool. I did my first year physics when I was a student in this lecture theatre. I vividly remember someone having a helium balloon and having a piece of paper hung from it so that it perfectly hung in the air and launching it from the back row. Lecturer was not happy. I don't remember what lecturer was talking about. It's probably thermodynamics or something. Okay, so this is my picture. There's an x-axis and there's a y-axis. I imagine it sort of falling. There's an x and y on my piece of paper and falling forwards. That's how I imagine it. And there's a z-axis there, and there's 1, 0, 0, and there's 0, 1, 0, and there's 0, 0, 1, and it's this pyramid here. But the lecturer drew it this way, just so you know. They rotated it around this way, and the lecturer drew it this way. So this x is round here, and they drew it this way. You can draw it however you like, or not at all. But the drawing is important. So the word tetrahedron means it has 4 faces, which it does. They're all triangles. Most of them are right-angled triangles. One of them is an equilateral triangle. So, I mean, obviously, you don't build a model of it in the exam. I just really felt like changing the mood for a minute. So what we want to do is we want to locate every point inside this tetrahedron. I'm just going to check that I really do. Okay, this is a function, which is a function of x and y and z. And so every point inside this tetrahedron, in space inside this tetrahedron, is going to have a function value of its own. And that function value is its current x coordinate, but it could have been something else. And so the calculation I perform on the coordinates of the points here to produce the function is write down the x coordinate. Okay, so I'm going to have to locate every point inside this tetrahedron. And so I need to do it one coordinate at a time. So I could imagine choosing let's do it directly from above, choosing the x coordinate, and then choosing the y coordinate, and then choosing a z coordinate. That's something I could do. Or I could imagine choosing the y, and then the x, and then the z, or choosing the z, and then the x, and then the y, if I wanted. If I was going to parameterize this, I could choose some other, completely other direction first, and then another direction, and then another direction. I'm not going to, because the x and y and z is the most productive way of doing this diagram. So if I choose my x first, the options for what x could be is everything from 0 to 1. That's my first thing I'm going to do. I'm going to choose the x coordinate. And on my diagram, the x coordinates could be anywhere from 0 to 1. There are less points that have an x coordinate near to 1, but that's not relevant. We'll deal with that in a minute. So once I've chosen an x, I don't have the same choices for what y is for every x. So I'm just going to look at just the base here. So just the base, that does not look at all like the word base, sorry. Once I've chosen this coordinate for x, just here, then I have to choose from among these options what the coordinate for y is going to be. And different x's have different amounts of y's that are able to be chosen. That's one of the important things I wanted to point out, that changing the value, choosing value of x changes what the y could be. Yeah. Okay. And so I need, based on the value of x, to figure out what the options are for y. And so I need a formula to tell me how many y's there are. And which means I need to figure out what this line is. So here's important piece of information 1. If you have a line with x-intercept A and y-intercept B, then its equation is x on A plus y on B equals 1. I don't know if you knew that. That's the intercept form of an equation of a line. You know the slope intercept form, y equals mx plus c, and you know the standard form, something x plus something y equals something. This is the intercept form of a line. In case you're wondering, it's a very useful way of very quickly coming up with the equations of lines. And so in our case, both of those things are 1. So I'm going to just get the equation of the line. X plus y equals 1. Every point on this line, the x-coordinate and the y-coordinate add to 1. But it's, x on 1, y on 1 equals 1. And so that means that the y-coordinate at any point on the line is 1 minus the x-coordinate. And so when I draw my picture, I can add to my picture the information that the y-coordinate at this point is 1 minus x. And so now I choose y between 0 and 1 minus x. So I started by choosing my x between 0 and 1. And now that I've chosen the x, the y goes between 0 and 1 minus x. How are we feeling? Cool. All right. And now that I've chosen my x and my y, I now need to choose my z. So here I am, this is the point x, y. And now I need to choose my z, and there's only certain options for what z could be. The closer I am to here, the more z's there are to choose from. The closer I am to the edge of this line here, the less z's there are to choose from. I need to figure out what the z coordinate could be based on the value of x and y, which means I need to know what the last z coordinate is, which means I need to know this plane as z equals. Are you ready? When you have a plane and it has x coordinate, x-intercept A and y-intercept B and z-intercept C, its equation is x on A plus y on B plus z on C equals 1. This is the intercept form of the equation of a plane. If we had 4 dimensions, then we could do this in 4 dimensions. It's one of my favorite things ever. I say that several times a day, of course, so, got to take it with a grain of salt, but I love it very much because I can believe that x plus y plus z would be 1 for all the points on this one here. Because it has to have an equation involving x and y and z. And at this point, x plus y plus z is 1. And at this point, x plus y plus z is 1. And at this point, x plus y plus z is 1. And so if 3 of the points satisfy the equation, all of them will. And if I stretch this out to be at point A, that's the same as replacing x with x divided by A. That's how you stretch functions out, right? You replace x with x divided by something. And so, yeah, that's my favorite. So the equation of the plane is x plus y plus z equals 1. And so the z is equal to 1 minus x minus y. And so that is what this z coordinate is just here. And so now I can choose z between 0 and 1 minus x minus y. Now, all of this decision-making process can happen very quickly, but I needed to do it this slowly to point out all of my thought processes that went into it. So let me just recap. First, I chose an x between 0 and 1 because that's what it said the x could be. And if I really wanted a picture for that, it would be these are the x's from 0 to 1. Just all by itself, they're the x's I can choose. And then I went to 2 dimensions and went, based on the x I've chosen, what y can I choose? And to do that, I needed to know what this line was, which told me what the boundary was between the 2 pieces. And I happen to know something about how to find the equations of lines. But you could have used the slope, which is -1 if you wanted. Slope is -1, the intercept is 1, so it would have been 1 minus x. That's a perfectly good way of doing it. And then once you've chosen that, based on the value of x and y that you've just chosen, now I have to choose a value of z. And so my integral is going to be, the x is going to go from 0 to 1. And then the y is going to go from 0 to 1 minus x. And then the z is going to go from 0 to 1 minus x minus y. And then the thing I'm integrating is x. And this is the integral of my function across the region. I've done something here which your lecturer probably doesn't do, but I can't do this successfully every time without doing it, is to remind myself what variable these numbers refer to. This is referring to x's. And most people are okay with it being, you know, this matching with this. Well, most people. Lecturers seem to be okay with this and that telling me what the x is, but I always forget and sub in the wrong one. And so that's just how I do it. Over in physics, they'll write the dx next to that there instead of writing it at the end to remind them what the x is, because technically it's all multiplication, doesn't matter when it happens. I can't cope with that, I need to put them at the end. Okay, and so now I would do this thing. So this integral I will do first. Now, I can cheat a bit if I want to. I can remove the x because it counts as a constant in terms of this integral and pull it out here. If I want, I choose not to for the moment, but I can. It would end up at this stage, I can't pull it out of this one because it's a variable there. So this x is a constant. A constant would have had a z attached to it. And this is going from z equals 0 to z equals 1 minus x minus y. And when z is 0, this is 0, but I'm just going to put it anyway. So I'm going to have x times z minus x times 0. Cool. I think I can cope with not expanding that out. I will have to do it eventually though. Do I do it now or later? Nope, I'm going to do it later. Okay, so if you're paying attention very carefully, you can skip this step, but be extremely careful. Subbing in 0 does not always have the answer 0, especially if you've got exponentials. Like if I had an e to the power of z, then no, that would not have been 0. It would have been minus x at this point. So just be really careful That just because there's a z equals 0 here doesn't mean this bit here will be 0. It's one of my mistakes that I make, so I watch out for it. How are we feeling at this point? So now I'm going to do this integral. And the x still counts as a constant in this integral. And so the x is multiplied on, so it will still be there afterwards. And the integral of 1 with respect to y is y. And the integral of minus x with respect to y is minus x times y. And the integral of y with respect to y is minus a half of y squared. And so, right. That is not fun. All right, so this really does come to 0 here, so that's good. Oh, yes. Look. Oh, look at this. There's a 1 minus x in both of these. And I'm left behind with a 1 minus x. Oh, that's so cool. Look, that's a 1 minus x squared minus half of 1 minus x squared, which is half of 1 minus x squared. Because we had one of them and we took away half, so we're left with half. Yay. There's still an x out the front. That's freaking me out, but that's okay. That's prettier. Oh. Don't like this x though. Don't like it. So at this stage, I would normally expand it out. Or I could use substitution. That would work too. Yeah. Or I could be very creative and rewrite it. And rewrite this x as an x minus 1 plus 1. That would do it too. Which one do you want me to use? I'm going to use substitution. So I differentiated both parts to u on dx, and that became a minus 1. So I can replace my dx with minus du, and replace the 1 minus x with u, and I can also replace x with 1 minus u. Oh, and I can replace x equals 0 with u equals 1, and I can replace x equals 1 with u equals 1 minus 1, which is 0. And so I've got that the integral I'm trying to find, u equals 1 to 0 of 1 minus u half of u squared minus du. Yeah. Now that minus and these will switch that around the other way, which is nicer. And then I've got half of u squared minus a half of u cubed, and that I can do. The half is still there, that'll go up to 3. The half is still there, that'll go up to 4. And I've got half times a third times 1 cubed minus a half times a quarter times 1 to the 4 minus 0 minus 0. Yeah. So I've got, what, a 6th minus a 12th, which is a 12th. Oh. Cool. So the average x coordinate of all the points in this pyramid is a 12th. I told you it would be close to 0. Yep.
If you ended up with like a little substitution 0 and there wasn't like a there, would that mean that you did something wrong?
No.
That's fine.
That's fine. I just was making it easy on myself. I could totally have kept this minus here and done from 1 to 0 and done 0 here, sub in 0 here, minus sub in 1 here, and it will still work. You're allowed to do integrals backwards. That's okay. You just got to be, it's just that I know my brain. If I had a 0 and a 1 here, I would automatically put the bigger number at the here and the smaller number here if I wasn't paying attention. And so I just switched it around. Yes. Yes, we do. This is not finally that we've just done half of the problem. That is a very important point. We haven't actually done the actual integral, the actual thing we're asked to do. All we've done so far is the integral of the function. We can't know the average value until we divide that by the volume. So, one of the vibes of this course is to avoid doing integrals if you can. It's a pyramid. I can figure out the volume of a pyramid. So I could do, you know, to find, you need the volume of the region. I could do this, you know, the integral x equals 0 to 1, integral y equals 0 to 1 minus x, the integral z equals 0 to 1 minus x minus y, dz, dy, dx of 1. That's how you do the volume of something. You're saying that across this entire region, at every moment, at every location, the thing I'm going to accumulate across that location, because that's what integrals are, they're accumulations of things. The thing I will accumulate is 1 centimeter cubed for every 1 centimeter cubed. That's why I put the 1 here. That is the rate at which the volume increases as I move past every point. I get an extra centimeter cubed for every centimeter cubed I go past. Whereas this is saying I get an extra x times the current x for every centimeter cubed I go past. So I could do this integral if I so desired. I do not desire to do this integral. Or it's a pyramid, right? The base is a triangle. Which has 1 here and 1 here. So the base area is a half times 1 times 1. Which is a half. And the volume of a pyramid is a third times the base area times the height, which is 1/3 times a half times 1. The base area was a half, we just figured that out, and the height of the pyramid is 1. And so that is 1/6. That is the volume of this pyramid. How do people feel about that calculation? It's a third, yes. In the same way that the area of a triangle is a half times the base times the height, the volume of a pyramid is a third times the base area times the height. If we were in 4 dimensions, the volume of a whatever a 4-dimensional pyramid is called would be a quarter times the base volume times the height. Goes up by 1. You've got to divide by that number. Yep, it's a third. Archimedes, I think it was Archimedes, some ancient Greek philosopher was famously had on his tombstone a picture of a pyramid inscribed in a cylinder, because it was the thing that he did, he was most proud of was proving that the volume of a cylinder is a third, the volume of a cone is a third the volume of the matching cylinder, which is the same as how pyramids work. So He was very proud of that. And he did it with integrals before integrals had been invented, like thousands of years. He imagined it by stacking up a whole lot of very thin slices, which is how we do integrals today. So just the coolest thing ever. Archimedes was a very clever man. But I can't remember my ancient Greek philosophers, so I can't remember which one is which. It's probably Archimedes. That sounds right. Archimedes was the one with the bath, wasn't it? Like with the eureka and running. Yeah. I'm struggling at the moment because I'm reading the Terry Pratchett book Small Gods, which has a big bit about Greek philosophers in it. In Discworld, Greece is called Ephebe, and yeah, they spend a lot of money on soap because they spend a lot of time in the bath. Okay, so we're not there yet. Just a second, and so the average value will be the integral divided by the volume. Which is a half. Ah, it's a lot bigger than I thought it would be. Twelfth is a half of a sixth, isn't it? Yes. Okay. Cool. If I'm worried, I can multiply the top and bottom by 6 to make this a 1, and then 6 divided by 12. Yes. Okay, that's a half. Okay. So do I really believe that? Is it? Oh, I've done something wrong then. Okay, just a second. Where did we go wrong? I feel like it's probably here. What's that? This integral here. What did you get? 24. Yeah. Oh, that's an 8, David. 2 times 4 is not 12. 2 times 4 is 8. There we go. Thank you. So it was right at the end. I'm glad I didn't have to fix it earlier than that. And a 6th minus an 8th is apparently a 24. Because that would be 4. Okay, cool. So it was a 24th divided by a 6th, which is a quarter. Oh, that feels better. My instincts are validated. So I was right to guess that it had to be a small number, and a half just seemed like a lot too much, because like a lot more than half of these points have less than half as their value of x. And so I would have expected the average value of x to be less than half. Yes, okay. As I say in every revision seminar, I wish in exams I had a team of people watching me to tell me that my answers were wrong. It'd be really useful. Yeah. But at least I was worried, and I should have trusted that. I should have trusted that worry and gone back to see if I had done every calculation correctly. Okay. Does anyone have anything to say or ask about what just happened? Or anything else? Yep. I have many tips on parameterization. I can talk about that. I've got 10 minutes to go. Possibly longer. I have booked the room for longer than the time. Okay. Just a second before I go on with that. I could possibly have shortcutted this a little bit if I had been paying very close attention. Can I do something? Just want to just as a, what if I was at this stage? Nah, it's not going to work. I was really going to try. I was just thinking this X can come out of here because it doesn't involve a Z. And it can come out of here because it doesn't involve a Y. But, and unfortunately, both of these involve X's, so I can't bring it out here. That's what I was going to do. But I was thinking that this is the area of a triangle. And so I could have figured that out from something else.
When you found the equation of the identities,
They were specifically the X, Y, and Z intercepts.
okay.
They were the X-intercept, the Y-intercept, and the Z-intercept. So that is specifically just for when you know all three of the intercepts. Yeah, so yeah, it doesn't work any other time. But it happens more commonly than you think. So I should just add that's the same here. Yeah. If there are any points on the plane, then you're probably going to have to start subbing them in or something. All right, parameterizing. I really thought I had it, but I didn't. Oh, that's all right. Ooh. One more thing. Here we go. Oh, yeah, it might work. If I had located it differently, I just want to try something else. If it had been Z that I was averaging instead of X, the answer should have been the same because it's symmetrical in every direction. But if it had been this, then no, still wrong. Okay, it's okay. It's worth a try. No, yes. No, sorry. I really am just hoping I could get like a triangle and then I know the area of the triangle, but no, I give up. So it's worth a try because that one's going to be like a 1 minus x minus y all squared. Then when I integrate with the dy, it's pain. Okay, that's okay. Does your lecturer put an E here? Do they say parameterization or parameter? Ah, cool. Possibly with a Z. Okay. So we get to choose how to spell it. Good. I spell it that way because it's like parameterization. Makes sense to me. Okay. So it's the same as what I said before. The point of a parameterization is to locate every point on your thing. So what I did before was a parameterization. It located every point in my volume, one coordinate at a time. It doesn't have to be one coordinate at a time, but for the purposes of integrating, you have to do it one coordinate at a time. The best parameterizations locate every point in such a way that making a choice for one parameter doesn't cause you to choose different things for the other parameters. So the best ones choice for one parameter does not depend on choices for other parameters. So the one that we did there was not the best parameterization for the volume inside a pyramid, because the choice for X changed what options were for Y, and the choices for X and Y changed what the options were for Z. But we were able to cope with it and do the integral anyway. But the best parameterizations, the choice for one parameter doesn't change what the choices for the other parameters are. If you're really good, you can do it that way. Yep. I don't think it's always possible, but if you're really lucky, it will be possible. I don't know if it was possible with the other one. Yes, it was possible. Maybe not. Triangles are weird. Pyramids are three-dimensionally weird. I'll have to think about that another day. That would be a fun thing to think about. Okay. Cool. And the other thing about parameterizations is that if you want to locate an object every point in a three-dimensional space, you're going to need 3 parameters. If you want to locate an object somewhere on a surface, you're going to need 2 parameters. If you want to locate a point somewhere on a line, you're going to need, or a curve, you're going to need 1 parameter. That's why we say that curves are one-dimensional objects, because they only need 1 parameter to locate every point. And the bestest ones are the ones where the boundary is easy to figure out from the other one. But I don't know how to say that in any better way than that, but I'll bring it up. So a surface has a curve as a boundary. If you choose your parameterization, if you're very lucky, you might be able to have one of the parameters that you use to describe the surface is capable of also describing the curve. That's what you want. Okay. I'll talk about that. Okay, so my tips are, my first tip is find a circle, or as many circles as you can. And the reason you find a circle is that a circle of radius r, centered at the origin, has parameterization r cos theta, r sine theta, where theta goes from 0 to 2 pi. I'm going to use a capital R because I'm not wanting that to be a variable at the moment. So the parameterization for a curve, which is a circle that is centered on the origin and has radius capital R, is r cos theta, r sine theta. You can choose your theta to go from minus pi to plus pi if it's easier for you. It doesn't really matter. But if you can find a circle on your surface or on the edge of your volume, it will make things easier. That's the first thing to know. And this is a classic parameterization. You're allowed to just go straight to it. Okay. And this find a circle will come back over and over because it may be that the R is chosen based on an earlier parameter as well. That's pretty much my only tip, actually. We may be able to come up with other tips, but this is my first, the only tip I can think of off the top of my head without doing an example. So W is the set of points X, Y, Z in R3 such that that. So what is this object? That is a Z there. Yeah, these are all good things. Tell me about the circle that you're seeing.
X squared plus y squared, R squared,
Mm-hmm. Cool. So the x squared plus y squared equals r squared. Classic place to find a circle. In fact, we should probably just notice this. This is x squared plus y squared equals r squared. Good noticing. But we're allowed to choose different values of z. And so there's a different circle for each z. You're thinking a cylinder? Yeah. Yeah, I mean, it might be. Well, let's just draw some pieces of it. So here we go. The fact that z has to be less than or equal to 4 tells me that I need the z is being chosen, and then from that I have information about what y's and x's are chosen. Well, that's fuzzy, sorry. No, that's covered by it's covered by this. So x squared and y squared can't be negative, which means that z has to be greater than or equal to 0. But if this had been a z squared, I would have needed to have the z being greater than or equal to 0. That would have been okay. So what I'm going to do is first figure out what this is. I know what this is because I made it up. So I know that if I choose different z's, I get circles. So choose z, I get x squared plus y squared equals z, which is a circle of radius root z. Definitely true. Good spotting. So at every height, when I choose a value of z, there is a circle there. And the other thing I know that is as z gets bigger, the radius gets bigger as well, which is what's making me think it might be a cone. So larger z, larger radius. Okay, so we're thinking that here's my x and my y, and when z is 0, the radius is 0, and then the radius is getting bigger and bigger. That's what we're thinking. And when you choose a z, you get a radius, and that radius gets higher and higher. Okay, cool. Cool. All right. So let me just choose just a particular value of x and y to see what it looks like when I slice it vertically. So I'm going to choose x equals 0. And then I'm going to get y squared equals z. I should have chosen y equals 0, but I'm going to choose y equals 0, sorry. So y equals 0 is this plane that goes through the x-axis. Y equals 0 is this plane because These are all values of y, and they are not 0, and this value of y is 0, so we get a plane there where y is 0. And we have z equals x squared, which is a parabola. So it's not a cone, it's a parabolic bowl. The official name for this shape is an elliptic paraboloid, but it's not a cone because it doesn't come to a point here. A cone, this would have been a straight line, which would have required you to actually have x squared equals z squared. So once upon a time, when this new version of, when the textbook for this was written, there was a whole section of Maths 1B on quadric surfaces. And so the lecturers who wrote the book assumed that you have seen that in Maths 1B, but they've cut it from Maths 1B since then, but the textbook is still assuming you know about quadric surfaces. So sorry, sorry on your lecturer's behalf. Okay, but that's what it is. It's actually a parabolic bowl. Something like that. And the z is naturally greater than or equal to 0 because of the z being equal to x squared. And the top here is when z is equal to 4. So it goes up this high and then it stops. And importantly, I only need 2 numbers to tell me where I am on this thing, because the z is chosen from the x and the y. And so that makes it a surface and not a volume. Yep. It's a surface because there is a single equation here, and you have to satisfy that equation in order to be on this object. And one equation in 3D causes a surface. So it's definitely a surface. Two equations in 3D would cause a curve usually. If it had been less than or equal to z, that would have been a whole other thing. That would have been a volume because it doesn't tell me exactly what x and y and z are. It only tells you where the edge of it is. Any questions or thoughts about that? Okay, but I have already found the circles. You found the circles. There's one at every height. And so I could parameterize this if I wanted by choosing z. Which goes from 0 to 4. And then once I've chosen z, I've got a circle of radius root z. If I wanted. Because the radius is root z. So I've got a radius cos theta, radius sine theta. That's how to make a circle in the xy plane. But the height is z. So that's a perfectly good parameterization. So my parameterization is root z cos theta root z sine theta z for z between 0 and 4 and theta between 0 and 2 pi. There are other ways to choose this, but that'll do the trick. So unfortunately, it is important to notice that different z's cause you to choose different thetas. There's nothing I can do about that. That's just the way this surface works. All right. Cool. If I didn't want those square roots in there, I could have called t root z, and then z would have been t squared, and I could have done t from 0 to 2, I guess. And that would have worked too. But I didn't know that until after the fact. So, yeah. I'm going to write that down though, because I did say it. That would have done the trick as well, and would have looked slightly cleaner, and my derivatives would have been easier if I had to differentiate it at some point. But it was the circle that made me do that parameterization. Yeah. Are there any parameterizations that people found specifically hard that you would like me to talk about? Oh, just a second. I have one more thing to say. The boundary of this surface is this circle just here. And I have carefully, because it is a circle, then I can say that the boundary is the circle radius 2 at height 4. And so the boundary has this parameterization. And so I was hoping to choose a parameterization in such a way that the boundary was just subbing in the value of z. And then I still had a theta left over, and that theta managed to tell me what the boundary was. So that's another thing. It's like, well, can I find the edge of it and call that, sine theta, cos theta, and then somehow change what the numbers 2, 2, and 4 are so that it gives me the rest of the surface using a different parameter. That's another decision that might be a useful way of dealing with this. Right.
So is that like kind of an instance of like using the Stokes theorem? It's gone from like
I'm setting up possibly needing to verify Stokes theorem. So at the moment, the parameterization is just a parameterization. It's just telling you where things are. But if you're going to use Stokes's theorem or prove that Stokes's theorem works for this surface, Green's is the one in the plane, isn't it? Okay. Then it's really useful to have your parameterization for the boundary to match up neatly to the parameterization for the rest. You don't want to have to parameterize it separately again from scratch. Okay. I can't think of any off the top of my head right now. Yeah. So just so you know, your cylinder, I just want to your cylinder radius R will have parameterization. Every Z will produce the same circle, and so you'll get R cos theta and R sine theta for the x and y coordinates, and then there'll be a Z to tell you how high you are. And that will be the surface of a cylinder. And then you have to choose where the top and the bottom is. Yeah. Whereas a cone So if the cone has radius r at height r, then the slope of this line is 1. And so the radius will be the same as the height. Will be the same as height everywhere, and so you're going to get r cos theta, r sine theta, r, which is bad. That's not telling me anything. Just a second. Z, 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 Z. Like that. Where Z goes from 0 to R. So if it has radius R at height something else, then you'll need to choose a formula for what the radius is based on the Z, based on the slope of that line. One last thing to say is that this will tend to have something more like this. It won't mention the Z in the formula with the X's and the Y's because the Z doesn't tell you what the choices are for X and Y. It's always the same choices for X and Y at every height. It always looks the same. And so it'll probably be something, you know, Z between A and B, right? But the bit with the X and Y won't do that. But in this one, the Z is related. What choice you can make for the X and the Y does involve a Z, and so it'll tend to look something more like something like that. It'll be a Z squared. I don't know if they just randomly pick ones that you haven't seen before. Yeah. Yeah. Because I specifically made one that had the height being the same as the radius at that top edge. Like the height is the same, radius R at height R. So. It could have been radius R at height H, in which case the Z would have been less than or equal to H. What you thinking? That's okay. I'm slicing this cone off at a fixed height. And it happens to be that at that height, the radius of the circle at that height is the same as the height that I'm at. That's just what it happens to be. And so if this R had been the number 10, then the Zs would have all been less than or equal to 10. Yeah. I should have done that. Classic thing to do if you're confused about what the variables are telling you is pick a number for them and see what it does then. Yeah. So I don't have any very many good advices, but the circle is the most productive thing I've ever known to find a circle. Even if that circle's not really there, like if you make a spiral, then you can look at it from above and go, oh, it's a circle. So there's got to be a cos theta sine theta somewhere. It's just that they might not have the same radius at the same time. So yeah. I don't know what they're going to do to you. I don't expect them to make you come up with a parameterization, but you may have to remember how the traditional cylindrical one works and the traditional spherical one works. And you tend to use those ones when the thing you're looking at is a cylinder or is a sphere. And so in a technical sense, this one I was using here I was using cylindrical coordinates here. I was going round in one direction and up in the other direction and out in the other direction. So I can do the volume inside this space by adjusting. So this only gives me the edge, the surface. I can do the volume inside it by trying to fill in all the gaps between the edge and the middle. And my favorite way of doing that is to multiply by P, where P stands for the percentage you are from the center to the edge. That's my favorite. It's not what the lecturer would do, but I'm just going to do it. So instead of W, I have like V is no, just a second. Yep, that's right. Oh, they would have been sneaky, I reckon, in an assignment or something, and they would have just combined them together into one thing. That is bad. Let's get a real eraser, David. X squared plus y squared is less than or equal to z, which is less than or equal to 4. So just another way of thinking about it. This is a function of x and y, which makes a surface. And I have the space between that function, which is a bowl, and the plane z equals 4. And so it's the same thing I had before. It's just that at the x, y coordinates of the bowl is allowed to fill in everything in between. I'm allowed to go at every z, every x squared, y squared less than or equal to z, which fills in the whole circle in the middle. And so what I can do is I can choose the height. Look at my dyslexia. Which is Z, and then choose the circle, which is the position around the circle if I want. Our height Z. And that would be the boundary. It would only be the edge. And then what if I wanted all the space in between? Well, I'm going to choose how far from the center I am. This distance here. But instead of doing it as a distance, which would be different at every height, so I could choose the distance. I could choose like R, a little r here, and say the R goes from 0 to Z, root Z. I could do that. But instead of choosing a distance, I could just say the percentage I am, the proportion of the distance to the edge I am. That is what's in my head. The percentage of distance to the edge. Because every height has the same percentage of the distance from the 0 to the edge. It always goes from 0 to 1. That's my favorite way of parameterizing anything that's got circles, is to just not use the radius, but yeah, use a percentage. But radius can sometimes be a little easier to interpret what it means. So I could have done, so this is like Z is from 0 to 4, theta is from 0 to 2 pi, and P is from 0 to 1. But I could have done something where I had done R cos theta and R sine theta and Z. And the R would have had to be between 0 and root Z. And that's the tricky bit, right? What you don't want, you can do it when you're integrating, and that's fine. So just as an, I could have said R cos theta, R sine theta, Z, which is proper cylindrical coordinates. And that would have been the Z is between 0 and 4, and the theta is between 0 and 2 pi. And the R is between 0 and whatever root Z is, and it will be different for different Zs. that's fine, and you can do it because you can encode that into your integral, as long as you do the R integral further in from the Z integral, but it doesn't work as a parameterization quite so well because this Z has to be chosen first, and so it's hard to write down. There you go. That's what I was meaning about earlier variables affecting what the later variables can be. So these ones make integrals easier because the numbers aren't affected by the other ones. Thoughts or questions? In that case, I'm going to stop there because this stool is very uncomfortable. Yep. Yep. Not off the top of my head. I don't have any particularly useful tips for complex calculus off the top of my head. Sorry? My memory of the residue theorem is faint at this time. No one asked me about it in the Maths Learning Centre, and so I this year, and so it's been more than a year since I've seen it. Not off the top of my head. Just let me check. The residue theorem is the thing that says, just a second. Residue theorem says that you've got your complex plane, right? And you've got a function and it has a pole. Is that right? Is that what they call it in this, a pole? At z equals z naught. And then it's saying that if you do an integral around the pole, you get a particular answer. Is that right? What does the residue theorem say? I don't remember.
It's basically, yes, you have a finite number of poles,
Mm-hmm.
like single points inside the region.
Yep.
Then the closed integral over that region, like C, of like f z equals 2 pi I, and the sum of the residues. And then the formula for residue.
What's the notation for residue?
RES.
Is there an F in?
RES of F and Z.
And what?
So like brackets. F and Z. F, Z.
Ah, so the residue of F at Z, in our case, Z0. Yeah. And then if you have several of them, you just add them all up. Yeah. Yep. Okay. And what does residue mean?
Well, it's to do like, I don't fully understand.
So the residue is the coefficient of 1 over Z in the Laurent series. Is it Laurent, like that? L-A-U-R-E-N-T? Cool. Is that the only thing that the residue is, or is there anything else? There's like a derivative thing, isn't there? Like you do. No, I don't believe it. Can I see? No, it is the coefficient. And it's also the limit as z goes to z0 of the k minus 1th derivative of z minus k z0 to the k f of z, all divided by k minus 1 factorial, where it has a pole of order k. Okay, cool. Pole of order k means that, so a pole happens when your function is not defined, right? Which usually means that the denominator has a z minus z naught in it. So if you can rewrite your function, so just, this is the notes. If you can rewrite your function as analytic function divided by z minus z naught power of k, it's pole of order k.
So the multiplicity.
Yep. And so you can either write your function as a Laurent series and pick out that coefficient, or you can do these derivatives. So I don't know. It depends, I reckon. So if your function is built from e to the power of stuff, then you have a chance, right? So if I had this, for example, this actually, oh, so it's not the coefficient of 1 over z, it's the coefficient of 1 minus z, 1 over z minus z naught. And I wanted the integral of f of z dz around C, where C is the circle, the length of Z is equal to 2, right? That's my problem. And so here is C, and here is 1, which is a pole, because the function isn't defined when Z is equal to 1. And so it's already written as analytic function divided by Z minus 1 squared. So it's a pole of order 2. And so I have choices. I can try and write this as a Laurent series, or I can do the appropriate derivatives. So I'm going to need to do, because it's a pole of order 2, I'm going to need to do the first derivative, because you always do, where if it's order k, use k minus 1. And so I can imagine that's not too bad, but I will have to use the quotient rule. All right. I don't know, that's okay. That's all good, because I have to multiply by the z minus z naught to the k first. And so this is the numerator, this thing here. Because they're saying that f of z already has a z minus z naught to the k in it. So if I multiply that, it just gives you the numerator of the fraction. Can I change the question? No, I won't, sorry. But nope, I'll just leave it like that. So you could say that z minus 1 squared times f of z is e to the z. And we're going to need the first derivative of that. Which is just e to the z again. And so the limit as z goes to 1 of that answer is e to the power of 1, which is the number e. And so therefore that is the residue. Residue of f at the point 1 is the number e. And so therefore the integral around c of f of z dz is 2 pi I times e. Yay. But I could have, so this one was easier today. But I could have done, or I don't know what's easier. I could have said, well, this has got a Taylor series, right? If I can write that Taylor series with a z minus 1, I'll be good. So this will be e to the z minus 1 plus 1. And that would be e times e to the z minus 1. And e to the z minus 1 is 1 plus z minus 1 plus z minus 1 squared on 2 plus forever. That's the Taylor series for e to the z minus 1. And so when I divide by z minus 1 squared, and there's the 1 over z minus 1 term, and its coefficient is e. Yeah, probably. Yeah. But I don't know. I could imagine an exam question which says find the Laurent series of this thing, and then do this integral, and you go, aha, coefficient was this, therefore that's the answer. So if you've already gone to the effort of finding the Laurent series, then that's the quickest way. But they're both choices. Yeah, but I don't have any other advice on that right now. Thank you. I really am going to stop now.